today's lecture is, oh, it's already lecture number 7. That's wow. Okay, and we have come a really, I think it's pretty long way, in the sense that we are trying to focus on the mathematical aspect of statistics, and we have already arrived at, yeah, it's a chapter 4.6. So I mean section 6. So it's almost, I think we're gonna finish pretty much chapter 4 today, and this is it. Okay, all right, and well, I'm shooting for maybe chapter 8 or something in the book. So that should be pretty good. All right, halfway. Okay, so what we are learning today is going to be quite all right in terms of the concept, but it's going to look pretty bad on screen because you are going to look at 2 more distribution that looks pretty bad. First one is the gamma, and the other one is the beta. The beta is the worst, I guess. Okay, so what we have for you this time is, last time we saw the normal distribution, things that you have been doing a lot, and for the normal distribution you have symmetric distribution, right? On left and right, something, I mean, or you can even go negative, you go positive, or you start from the mean and then you go one way and the other, sort of symmetrically, right, on both sides. However, there might be some nature of some data that has like a skewness in the distribution. So it has a non-symmetric properties built into the distribution. So sometimes you need some distribution that reflect that non-symmetrical nature of your data. Okay. And sometimes you might even have to deal with only positive number, actually most of the time, actually, right? So there will be some non-negative functions that showcase some skewness in your distribution, and that is something that actually going to reflect in reality. So there will be some connections with the actual scenario that we're going to see. Okay, so we'll come back. You can read through this. There are some situations that has this kind of distribution. Okay, for example, the length of time that something is going to fail, or the wait time, or the queuing at the booth, or something like that. It has some sort of a skewness built in the distribution. Okay, so let's start from the first one, the gamma distribution. All right, take your deep breath in. This is it. And this is the business that we're going to do a lot today. It's actually the main focus of today's lecture. It's the beta distribution. All right, guys. I don't know, have you seen this before? Maybe, maybe not. But if not, this is it. Is the y to the alpha minus 1 followed by the exponential? Nah. All right. Of course, it's always a negative exponent, because if it's positive, it will sort of explode, right? So usually you have an exponential decay. So it's a product between a polynomial. You think of it like a power function multiplied by the exponential decay. So that is competing between the two. All right. And of course, there are some factor in the bottom part. Okay. So there's a beta to the alpha, and that is the gamma of alpha. So if you look at this one, you already can see that this is a distribution that's sort of like has 2 parameters built into it, the alpha and the beta. And we always assume they are positive number. Okay, we don't deal with the negative one, because I mean, from the look of the function, if you deal with the negative one, you're going to have some divergence of the function, so it won't work. Okay, so the complication comes in not only the shape of the function itself, but is the gamma. This is the capital gamma, gammaใหญ่. So the gamma is a function of the alpha, and it turns out is the integral. Of course, it's the integral of the one that has the same shape as whatever on top, right there. And then you do the integral everywhere in the positive region of the space. That is the gamma of the alpha. This gamma has a name, and that's a name correspond to the distribution. It's a gamma function right there. Okay, and the good thing about this one is you can see right away, if you try to calculate the gamma of 1, the gamma 1, you can just plug in alpha equal to 1. Okay, let's do this quickly. So for the gamma 1, the reason for doing this just to get used to the function. myself, I'm not using a lot of this. So every time that you want to refer to this, you can refer to this definition, no problem. You don't have to memorize it. But of course, as usual, if you do it repetitively, right, when you prepare for the exam or stuff, I mean, this function probably gonna stuck in your head. But if you see this like once a year and things like that, so don't worry, just come back to this and then just try. But at least we just have to understand the structure of the function. I think that's the goal. Okay, so for the gamma 1, you do the integral from 0 to infinity of y to the 0, of course. You substitute alpha into it. And then there is e to the negative y dy. Okay, and of course, this one turned to 1. You only have the exponential to integrate. And everyone knows how to do this. Integral of the e to the negative y, you still get e to the negative y, but with a negative sign there. Okay, and then you take the lower and upper limits, and that's it. You substitute infinite in there, you get 0, subtract to the negative e to the 0, and that is 1 right there. So that's give you the starting points. Give you the starting point. Now, let's think of this like a warm-up of today's mathematical procedure. That is an important property of this gamma function. And this is something that I think you should see it once or twice in your lifetime. This is a recursive formula. When I say recursive, means one value of the gamma function can give another value of the gamma function with a different parameter, of course. Like this one, you can see that if you substitute or if you have gamma of alpha minus 1, it can lead you to the gamma of alpha. So what I'm saying over here is, so let's give it a shot. If I have gamma of 1, we already calculated that, right? Okay. So that means this is the gamma of 2 minus 1. Just write it like that. So if you put it in there and use this recursive formula, what you're getting is you're going to say that the gamma 2 is going to be equal to 2 minus 1 times gamma 2 minus 1, which is gamma 1. And that is just 1. That's perfect. So that's mean you can use this gamma of 1 to be your starting point. And with this recursive formula, you can get to the gamma 2. Once you get to the gamma 2, you can now move on to gamma 3 is going to be 3 minus 1 times the gamma of 2, of course. But the gamma of 2, you already got it, is 1. So it's going to be 2 times 1. That's your gamma 3. And now you start seeing something, yeah? If I try gamma, if I try gamma 4, is going to be 4 minus 1 is going to be 3, and a gamma 3. But the gamma 3 you already found out is 2 times 1. So it's going to be 3 times 2 times 1. Now you start seeing something, yeah? And then if I keep going, gamma 5. Oh, yeah. Okay, let me zoom in. Sorry, guys. You might not be able to see this if I don't zoom it in. So if I try gamma 5, yeah. So it's going to be 4, gamma 4. But you already figured out that gamma of 4 is 3, 2, 1. So it's going to be 4 times 3 times 2 times 1. See that? And that is it, guys. It turns out the gamma function can actually give you connection to the factorial right there. And from this conclusion, you get this expression right here. The gamma of n is actually n minus 1 factorial. Hey, wow. Have you seen this before? Oh, quiet is very peaceful. หลังจากที่เริ่มสอนมันจะครบ2 เดือนแล้วเริ่มคุ้นชินกับความสงบของการเรียนออนไลน์มาก Very nice. Okay, cool. All right. So that's good. So that is something that need to be pretty much sort of give you an overview of what the gamma function is. All right. And what are we going to do next? All right. We haven't talked about the distribution just yet. So let's keep going. All right, there we go. So there is a shape of this curve. So if you try to plot this distribution function, okay, so these are the shape. And I have a link to that actually you can figure out your own. You can type like gamma distribution plot or something like that. But this one just the one that I found out online. So I sort of put the link on this page. So you can try go to that page and then you allow to pretty much sort of like adjust your parameter. Okay, give me 1 second, guys. Map department PM โทรมา Okay, flash news here. โอ้กำลังคุยกันเรื่องข้อสอบ there is this is a quick announcement, but I'll put the announcement on our classroom again to be an official one. It turns out this course is going to be accredited by the IFOA, yeah. So they will not allow to do the online exam. That's pretty much sort of maybe some requirements there. So you guys need to do on site. Now, because the exam paper itself need to be approved by the IFOA as well. So the exam date turn out to be pushed to the mid of March. That's according to PM just told me. Because we need to process the exam paper first. So like we have to send the exam paper to some place in British England or something like that, and then they just approve back and then use that as an exam paper. So that's why I said there was some sort of like complex process I have to go through that I haven't done before. So it's kind of confusing for me. But that is it in the sense that answer your questions first. The exam probably not probably it will be an on-site exam. Okay. And the second one is the date of the exam is not going to be the first week of March. It's going to be probably, according to PM, is somewhere around 18th of March. So we're going to have to work on something about, how to prepare for that because we cannot stop studying, I guess. So it will be like some lectures that gonna go beyond the midterm, but the midterm is gonna cut somewhere. Okay, so I'm gonna announce about the material that we're going to cover in the midterm at the end of today's lecture. But my plan was I'm gonna end the the content of the midterm within this week actually. So this my plan was this supposed to be the sort of like the line that's gonna cut sort of like, hey, the material that we're gonna cover is just up to chapter 4 in the textbook. Okay, that sounds reasonable. I'm thinking, yeah. Okay. All right. But if there are some adjustment or changes, I'll let you know. All right. Okay. Oh, I know it's crazy time. It's kind of weird. So many things going on. อาจารย์ก็มึนๆเหมือนกับพวกเราตอนนี้ โอ้มันหลายอย่างเหลือเกินมึนมาก Okay. All right. Just let me know if you have any concerns or you sort of worried about anything, something. And I think understand that some of you from the industrial math, I guess, you guys probably wondering about, hey, John, I'm not supposed to have to go through any IFOA. What should I do? I'll think about that and how to proceed in terms of how to manage those properly. Okay, sounds good. So there will be some maybe some differences between the 281 and 286. Okay, and actually from those of you that's in the actual programs and from the industrial math programs. So there might be some a little bit of difference in terms of the format or the the evaluation scheme. I'm not so sure at this point. Okay, but I'll keep that in mind. Okay. All right. Woo. All right, come back to this one. All right, where were we? Okay, so you can try this link and try to look at the plot of the gamma distribution with various value of the alpha and the beta. Okay, if you try those, the thing is, if you can do it close by, actually, I can do that too. Can I? Oh, this is my Zoom. So sorry. So I can click that. แต่ก็งงไปคลิกตรงไหนก็ไม่รู้ Oh, it doesn't work in here. Oh, no, so this is PDF one. All right. Anyway, so you guys can try this and see how it goes. I think I wanted to show you and ทำไปด้วยกันแล้วกันเนาะโอเคเดี๋ยวแป๊บนึงนะ Okay, let me try this. Here we go. You guys see this already? So with this distribution, you can test by putting like maybe 1 and 1, for example. So it will give you the plot right away. Okay, that's cool. So you can adjust this 2, and then you get the shape 3, 4, 5, 6. See that? So as you can see, when you adjust the alpha, things are pretty much changing the shape. Okay, and it's actually is going out to what sort of like away from the origin, and it may look a little bit more symmetric when alpha get a little bit larger, but it's non-symmetric anyway. You can see that there is some skewness going on the right. Okay, so that's why changing the value of the alpha, changing the shape of the gamma distribution. So that's why sometimes they name this alpha to be the shape parameter, because different alpha give you different shape. Okay, and the beta, you can try that. Okay, let me maybe choose alpha to 2. This is the shape of the alpha equal to 2. And now you can change the beta to 2, beta to 3, beta to 4, beta to 5. Do you see, notice something here? The shape does not change. But if you look at the scale on the left and in the bottom, okay, let's start again. 1, see that? Look at the scale here. Okay, look at the scale. And now I go to 2, bam, scale changing, but the shape does not. Bam, 4, 5. So that's why the beta can be named scale parameter, because it's only scale the x and y axis, all the values, distributions, and all the stuff, but does not change the shape of the distribution. Okay, cool. All right, so that's what it is. And I have to share this again one more time. Confusing what I'm doing here. Oh, check camera. Share the wrong one. Okay, it's like a double angle. Okay, here we go. All right, so I hope you guys see what it means by beta is a scale parameter and the alpha is a shape parameter. This is what it means. Okay, However, there's one thing that's it's very interesting for the alpha equal to 1. Do you notice something here? That it has no, sort of like there's no maximum in the middle. It starts from the top and is monotonically decreased. That is alpha equal to 1. But for other alpha, you have some sort of like a increasing in the first portion of your distribution and then peak out somewhere and then dying down. Okay, so that's what it is. It turns out there is something special about the alpha equal to 1 that we're going to look at. Okay, and the alpha doesn't need to be integer. That's the thing. Okay, but the bad thing is once the alpha is a non-integer, your integral will go crazy. I mean, not crazy, but you cannot do this integral when the alpha is kind of weird. Okay, when this alpha comes out as a non-integer number, your integral needs some numerical techniques or some tables or something that you have to have by your side to evaluate those integral. Okay, so that's what it is. All right. So that's what we, but of course, in our course, we're going to stick with integer alpha and beta for simplicity. Okay. All right. Now, so for the mean and the variance, of course, just like in the usual case, every time you are given the probability density function or distribution function, you will be able to evaluate the mean and the variance just like before through the figuring out of the expectation value, the expected value of y and y squared. And from there, then you can figure out the mean and the variance. Okay. And now you already see that it's here, blank space. พร้อมยังมาทุกคนอาจารย์ออกข้อสอบข้อนี้เลยได้ไหมอ่ะจริงถามพวกเราก็ไม่รู้นะเพราะเดี๋ยวนี้อาจารย์ออกเองก็ไม่ได้นะอาจารย์ต้องไปดู IFOA ก่อน โอ้เป็นการสอนที่แบบยอมรับว่าเทอมนี้เหมือนมันไม่สามารถแบบนะอยากสอนอะไรก็สอนนะมันต้องมี some standard and stuff that I have to adhere to so it's kind of tough โอเคมาพวกเรา try it figure out the expectation value or the expected value of y โอ้โหงานเนี้ยระเบิดดูจากฟังก์ชันหลายคนอาจารย์เลยขี้เกียจเผื่อพวกเราจะขี้เกียจที่จะ slide back นะ so I put those two expression of the gamma distribution and the gamma function for you guys on the right so you don't have to sort of like slide back and forth okay guys first like a breakfast mathematical breakfast here find me the expected value of y and of course expected value of y square once you know these two you can figure out the mean and the variance ทุกคนทบทวนตอนนี้ถึงจุดที่พวกเราทุกคน no problem with the expected value so every time you want to figure out the expected value is okay let me use the black color here is the expected of y of course you plug in the y multiply by the probability for the continuous type you put in the probability density function and then you do the integral everywhere all right that is your expected value of y and I mean you can start this for any expected value already if you want the expected of y square you put the y square in there all right here comes the crazy part บอกอาจารย์เอาจริงเหรอ yeah plug in this f right there. Okay so I just put the integral form in here so the density function is what inside so just plug in that one so you're gonna have y to the alpha minus 1 okay e to the negative y over beta all right divided by beta to the alpha then the gamma of the alpha dy integrating everywhere คำถามช่วยอินดิเกตตรงนี้ให้อาจารย์หน่อย มาทุกคนสู้ๆ okay when I say integrate this for me it's not gonna be that bad because if it's bad I'm not gonna do it นั้นทุกคนลองนิดนึงให้เวลากับมันนิดหน่อย think of it like this is like once in a lifetime thing you're supposed to be able to sit down and try a little bit of this have it sort of like register in your brain that I have done this before. But it's more like a manipulation here. So you have sort of like to look around a bit. Okay, very good. So actually, it's easier than you think. For those of you that look at this integral and just like sort of like shy away from this, like I don't want to deal with this crazy integral. No, it's not too bad. Here's the key. The y is already sort of come with the y to the alpha minus 1 inside your distribution, right? So once you multiply in, it's going to change your integral by a bit. When I say by a bit, just to be clear, I'm going to write it like this. It's alpha. You have extra y here, so you plus 1 and then you minus 1. You guys with me? Now start to get a clue, I guess. See that? ริ่มได้ไอเดียยัง? Not bad. The reason it's not bad because when I sort of like deposit extra y into it, you add 1 to your alpha. Think of it that way. So when you add 1 to the alpha, you think of it, Ajahn, if I add 1 to the alpha, it just means it's trying to represent the distribution that has just a different value of alpha. So if I am able to rearrange this integral to have it look exactly the same as the look exactly as the same as the gamma distribution, but different parameter of alpha, should be like, I'm okay. Because the integral might just give me something very simple, but just different parameter alpha. Okay, so let's try that one. So I'm gonna pull this beta to the alpha out first. เอานะโอเคไปเรื่อยๆนะอาจารย์พยายามดู like step by step here. So I have the beta to the alpha, gamma alpha, and now I have the integral in here, y to the alpha plus 1. The reason I write plus 1 just to make it obvious. Here we go. Just put parentheses on it. E to the negative y over beta. It has nothing to do with the alpha. And then dy. So what should we do here? So what should we do is if I have beta to the alpha plus 1, you guys with me? Along with the gamma of the alpha plus 1, this integral eventually will give me 1. Because it's just another gamma distribution with the parameter alpha to be alpha plus 1. เข้าใจไหมโอเค But of course I cannot just divide this alone. I just have to multiply back. So that means it's like I divide and multiply by this beta to the alpha plus 1 gamma alpha plus 1. Yeah, สนุกไหม? That's not too bad. And then I can just call this whole thing here to be just evaluating the gamma distribution everywhere. And of course, that integral has to give me 1. So now I can turn back to my black ink here. So at the end, what I'm getting is here, beta to the alpha plus 1, gamma alpha plus 1 over beta to the alpha, gamma alpha. This whole thing turns to 1. All right, and this is cool. Beta to the alpha cancel everything out. I mean, not everything. Cancel beta to the alpha out. So you're left with just the beta on top. And you already remember this. The gamma of the alpha plus 1 is actually just alpha times gamma alpha. Or you can think of this, the gamma of the alpha plus 1 is just alpha factorial if you want to. So you divide it out by the alpha minus 1 factorial. So what you left here is just alpha. And that's done with your expected value of y. Okay, so as you can see, well, from what we have seen in the past, usually when we try to get to the mean or the variance, usually we haven't had to attack the integral directly. Usually there will be some manipulation and there will be some pop out from those integral that give you 1, give you 0, or you can throw away some parts and all stuff. And the rest is kind of like, okay, just use the known properties of the distribution and be done with the calculation. โอเคสนุกไหมอย่างงี้โอเคไหมพอได้เนาะ okay so if this is good don't forget to try this must try อันนี้พยายามเชิญชวนนะเนาะลองแล้วกันสนุก and try to get to the alpha beta square for the variance it will be fun but it's in the same line of thinking like this it's just manipulation of the integral not evaluating the integral directly all right cool any questions so far all right I think it's pretty good and I think once you've seen this I mean it's gonna be stuck in your head forever all right next there are some two extra distribution that sort of like spring out from this gamma distribution. So you can think of the gamma distribution to be like a big family of distribution. All right. But then among this, there are two special, well, sort of like unique two, well, not unique because they are all gamma distribution. There are two special ones that we will eventually take a look at this many times in the future. First of all, it says that if you can pick your alpha to be some parameter that we're going to name them the degree of freedom nu, I'm pretty sure they call the nu here. I don't think it's the v, or is it v? Yeah, I just realized that I'm not so sure anymore. All right, but I think this is a Greek parameter. I think the textbook tend to use the Greek for the parameter here. So is the nu over 2 and the beta equal to 2. So that means when you freeze your beta value to be 2 and the alpha can link to another parameter that we're going to name them the degree of freedom. And this is the chi-square distribution. So the chi-square distribution is a special gamma distribution when the beta equal to 2 and the alpha is some number, but then we can re-express that number in terms of the half of the degree of freedom. Okay, anything that has this distribution that we're going to call them the chi-square random variable. We're going to deal with this later. Okay, but the idea is, as you can see, this comes in the theorem in chapter 6. We haven't get to that part just yet, but just give you the idea because you have done many statistics course. Look at this one. If you have y1 y2, there are so many random variables, and you define a new random variable to be this. Well, hey, John, this is the standardized stuff. Yeah, you do the y, subtract out some parameter that is supposed to be the mean of that group or something, or the mean of that sample, and then divided by the standard deviation inside that group I, on and on. Then you take those z, you square them, and then try to find the sum of these. It turns out these summation of the z square will have the chi-square distribution with n, which is n is the number of the groups that you try to sum them up to be the degree of freedom. Yeah, isn't that cool? All right, so it's pretty much natural that in the future, in the near future, of course, when you do some random sampling, and then you have a group of sample here, you try to evaluate the mean of the sample, standard deviation of the sample, so you get some sort of like information about this sample. But then you move on to another one, you do some experiment again and again and again and again, and then you try to figure out, hey, what are the z value among these groups of samples that we have built upon, and try to calculate the sum of the z square. From the theory, we say that distribution of this parameter, or this newly defined, we haven't defined anything yet, but the summation of the z square will have the chi-square distribution, something like this. All right, so we're going to be able to face this eventually, but just for the purpose of today's lecture, the chi-square is gamma distribution when beta is equal to 2 and the alpha is half of the degree of freedom, or I mean, you can think just it's alpha. Okay, very good. And just by using the result that we already learned, the mean is alpha beta, the variance is the alpha beta square. So you can figure out that, hey, the mean is just the degree of freedom by itself. Alpha beta is already simple. Okay, so it's just nu over 2 times 2. So that's a nu right there. And the variance is alpha beta square. So alpha beta square, alpha is just nu over 2. Beta square is going to be 4. So it's going to be 2 nu. There you go. All right, so that's the first kind of gamma distribution that eventually you're going to face uh, a couple times more later. Okay, now another one, the special one, and this is so good, is the one when the alpha is equal to 1. And we already saw this from the plot. When the alpha is equal to 1 is a monotonically decreasing function. And it turns out, if you substitute this one back into this, whoa, Adan, yeah, we did that. When you substitute alpha equal to 1, this term disappear. Okay. The gamma of 1 is just 1, so this one also disappear. The alpha up here is 1, so that alpha is pretty much disappear. So what you have left? You only left with just the exponential part of this gamma distribution. So that's why this is a special case. We say that when you deal with the alpha equal to 1, you get the exponential density function. And alpha disappear, the gamma function disappear, the power part disappear, and this is it. This is the part that we just got left. Okay, and you only down to single parameter beta. So of course we can say that once you pick alpha to be 1, the random variable y is said to have exponential distribution with parameter beta, and always positive, of course. All right, so today now we learn, well, we can say 3 distribution if you want. The gamma, which is the grand big daddy of everything, and then you learn 2 children of this gamma distribution, the chi-square and the exponential. Okay, and once again, using the alpha beta, the alpha is 1. So the mean of the exponential is going to be the beta and the alpha beta square. And that will give you the variance of exponential distribution to be just beta square. Okay, chill ไปเรื่อยๆเลยเพราะฉะนั้น let's try this. This one is important. I want you guys to try this. อันนี้ลงมือเลยคือถ้าใจอาจารย์จริงนะอยากออกข้อสอบข้อนี้มากเลย It's like not too hard, not too simple, and it has something to showcase in terms of like, hey, this is the cool property of the exponential distribution. Okay, everyone, รบกวน try this. มาทำไปด้วยกัน So, okay, let me read the problems together, yeah? Suppose y has an exponential probability density function, okay? So that's no problem. You already saw that. Okay, let me write it on the side. 1 over beta, e to the negative y over beta distribution right there. So they want you to show that when a and b are positive, so of course we only deal with the positive value of this mainly by default, the conditional probability of y when it's bigger than a plus b, given that y is bigger than a, is the probability of y is greater than b. มา they just want you to just show it ทุกคนลองดูให้เวลา5 นาทีเฮ้ยทุกคนยังอยู่กับอาจารย์อยู่ปะเนี่ยโอเคยังอยู่นะโอเคผมวันนี้ไม่มี communication เลยนะทุกคน like one way communication นะทุกคนยัง alright อยู่นะไม่ได้มีปัญหากับอาจารย์นะโอเค very good ทุกคนได้ยินเสียงอาจารย์ชัดเจน โอ้ให้อาจารย์ไม่ได้งอนอะไรอาจารย์นะ มาทุกคนทำหน่อย so you want to figure out the conditional probability on the left and try to compare the value that you got to the right. Okay, for those of you that's familiar with this, we can start from, okay, ตรงนี้เนาะ it's just a probability of y greater than a plus b and probability of y greater than a divided by probability of y greater than a, something like that. Oh, actually, I can just put it in the bracket here so it won't get confused. Here we go. And yeah, something like that. There. So you want to figure out the probability when y is greater than a plus b and y is greater than a. And then you divide it out by the probability of y greater than a. That's just a conditional probability calculation. Okay, แล้วก็เป็น starting point เนาะทุกคนก็รู้ว่าเฮ้ยอาจารย์ of course intersection between y greater than a plus b and y greater than a. The intersection is just going to be y greater than a plus b anyway. All right, so I think you get up to this point now. Very good. All right, now your job is try to figure out the probability of the numerator and denominator there. เดี๋ยวอาจารย์ขอไปเอาเครื่องดื่มมาหน่อยนะคอเริ่มแห้ง เป็นไงได้ไหมจ๊ะโอเคขออนุญาตโอ้โหนี่คืออะไรขอโทษทีกินมันคือนมข้าวโพดนะอย่างโอเค all right so what you want is to try to figure out the probability when y is larger than a plus b. Okay, now you're gonna have to practice a bit now. So you have to do the integral of the distribution function itself, 1 over beta e to the negative y over beta dy. Okay, and you want to go beyond a plus b. So it means you're going to start from a plus b all the way. Okay, very good. Now you have to practice your integral a bit. Whatever constant we can pull out from your integral. And now this is your stuff now. You can do substitution techniques or whatever things that you're familiar with. All right, but it's just an exponential integration anyway. So it's not too bad. So what we can do, my way of doing it, I prefer because this is so simple to do. You don't need to do full substitution if you don't like. So what I'm doing over here is, I don't อันนี้เผื่อไว้นะสำหรับใครที่ชอบเทคนิคนี้แล้วกันอันนี้อาจารย์ just show you how I'm doing this integral. So because what we want is the y over beta. We want y over beta. But the integrating variable is just y. It's missing the beta. So what I'm doing is I divide it out by beta and I multiply out with the beta. That's what it is. Something like that. Okay. Or actually, I can skip to this one by saying that I'm going to drag this beta from the outside to the bottom part of this y. So you see what I'm saying here? So what I'm getting from this quick integral right here is just I'm going to get e to the negative y over beta dy over beta. Something like this. All right? Simple things that might help you make less mistakes in terms of like missing a factors or something like that. And when you look at this one, then now you can think of this like e to the negative, something like that. All right, it's just like e to the negative x dx. And then you can do integral everything under y over beta integrating variable อันนี้ไม่รู้ช่วยหรือเปล่านะแต่คิดว่าเผื่อใครชอบสไตล์นี้เนาะ Okay, so this is what we got. So we just say it's going to be the integral of this one is going to give you the negative e to the negative y over beta เนี่ยมันก็คือมันก็ดูง่ายขึ้นน่ะไม่รู้นะสำหรับอาจารย์รู้สึกว่างั้น so it seems to be like it looks cleaner and it seems to be like a quicker way you can do everything in one line you don't have to say hey let's call u to be y over beta something like that. All right, and at the end you substitute the lower and upper limit there. All right, substitute the upper limit is the e to the negative infinity, which is 0, so that's good. First term is 0. The second term, there is a negative e to the negative a plus b over beta. So at the end, what you get from the probability of y greater than a plus b is just an exponential, e to the negative a plus b over beta. That's for the numerator. But once you do this, the denominator will look exactly the same now because it's greater than a. Okay, you don't even have to redo everything again because the only thing that's going to change is just going to be your lower limit of integration. Okay, so you can see right away, you're going to go through this integral and you're going to end up with the same result, except replacing the a plus b with just the a. You guys with me? All right, now come back to our business here. We want to evaluate the conditional probability. So the conditional probability that we looking for, let me rewrite this one again. It's just going to be the ratio of these two, e to the negative a plus b over beta divided by e to the negative a over beta. And as you can see, that a will cancel with this. I mean, cancel mean go all this will disappear. You will be left with just e to the negative b over beta. And if you think backward, well, Ajahn, what you're getting over here is just this, is just that. So that means this is going to be the same as the probability when y is greater than b. Nice. So you already shown this relationship right there. ทันไหมเอ่ยโอเคเนาะ All right. So what's the point then? Okay. First point, I just have to make sure that you know how to do the integration of those exponential functions. And of course, the second one is you require to calculate the conditional probability. And the third one is you have to know how to put your limit of integration correctly. In this case, you know, a plus b all the way to infinity, or a to infinity, b to infinity. So you know the range of your integral to figure out the area under the curve properly. And the last one though, when you look at this one, what does this mean? This say the probability that the y has the value bigger than a plus b. But given that it's already bigger than a, it's the same as the probability that the y itself is larger than b. So if I try to draw like a diagram of timeline, if you think of this as time, you're starting from a, this is time b, keep going like that. The probability, given that y is already bigger than a, so it means bigger than a, it means this timeline, we pretty much this timeline, yeah, is already go all the way up to a. And this one, given that this is already bigger than a, so I mean you're already interested, oh, let me use highlight. So you're already interested in the value that's go beyond a, given that here, this is your interest right here. But then you want to figure out the probability that y is larger than a plus b. So that means you want to figure out the probability that everything fall within this area right here. Given that you're already beyond a, what is the probability that is beyond a plus b? So it means it's to the right of b. But it turns out on the right hand side, it say about that's all right. It's going to be the same thing as probability of y greater than b. Just like this. So it's just like, hey, you can reset your clock and say about, hey, let's call this time 0 again. And then you recalculate everything starting from B. Same thing. So we call this, I don't know, have you heard of this one? Maybe once already when you learn exponential distribution. This is what it means by memory less property. When it's memory less, it's a memory less. It means it doesn't care what has already happened in the past. Every time you want to calculate it, let's restart it again. Okay. It has no memory. Whatever happened before B, I don't care. Start again. Okay. All right. So this is the property of the exponential function. It doesn't matter how long has been gone. If you would like to start your experiment now, your distribution stay exponential decay. So that's why this one reflects pretty good in terms of, like, for example, um, you can say like the people that try to show up in front of the convenience store, for example, right? So it doesn't really matter how many time that you have to wait for the first people to arrive, but the probability that the second people comes in is still exponential decay in time or something like that. So you can think of this in terms of the independencies and all the stuff. It has no dependency between whatever happens before the events gonna occur. Okay, sounds good. All right, so that's the nice property of this exponential distribution, is a memoryless property. Okay, very cool. All right, and this, you can read through this. I put a highlight on in the text that describe some realistic events that might work well with the exponential function. For example, the length of life of electronic components, like something is gonna dead at what time, we don't know, but we assume that it's exponential decay in time and stuff like that. Okay, and the fuse or something arrival and all this stuff use exponential distribution. So you can read through this. Okay, now there's one more that I want you to try. So let's do this just to sort of like quickly practice your familiarity with the exponential function. Let y be an exponentially distributed random variable with the mean beta. Define a random variable x in the following way. อันนี้อาจจะดูซับซ้อนนิดนึงนะแต่ let's say ว่าได้ไหมเนาะ x is just a number, okay, when y fall between k minus 1 and k. Okay, so that means it seems like you want to do like a binning คือหมายว่าเหมือนกับที่เราเขียนโปรแกรมเนาะ it's like binning in the computer programming language. So you have some sort of something that's continuous, but then you want to say, hey, I want to slice this into a block. If it fall within the first block, I call this 1. Second block, I call this number 2. Third block, I call this number 3. That's the idea. So you slice your y into block, all right? And if the value fall between k minus 1 and k, you're going to name this that k. All right. So it means, for example, when y is between 0 and 1, that's when x equal to 1. Something like this, right? And then when y is between 1 and 2, then that is corresponding to random variable x equal to 2, on and on. So this is what you're trying to do. Okay, so what they want to figure out the probability distribution or density, or it's maybe it turns out to be a discrete one, but anyway, it's the probability mass function of the x. Okay, let's give it a shot. อันนี้น่าสนใจอันนี้ทำไปด้วยกันแล้วกันเนาะเพราะว่าทุกคนอาจจะงงว่าอาจารย์ต้องการทำอะไร Okay, I found this one very interesting, so that's why I put it here. Once again, just to practice your exponential distribution calculation. So probability when x has a value of k can be calculated from the probability that y, okay, because it's inequality, so y fall within k minus 1 to k. There you go. Very good. And because we know it's a continuous random variable, right? It's go all the way. So what you can do is you can do the probability when y is greater than, or because it's less than. So you get less than k, and then you subtract out the probability that y is less than k minus 1. There you go. อันนี้คนทันนะเนาะ all right, so if you draw like a timeline, so this is k minus 1, I'm sorry, k minus 1, k plus 1. So you want to figure out just the probability that it fall within this k minus 1 to k. So you can take the probability all the way to k, subtract out the probability all the way to k minus 1. You're going to get whatever you want between k minus 1 to k. Okay. There you go. All right. And now, because these y are exponential, so what you need is, of course, for this one, you're going to have to do the integral, okay, from, okay, let me say 1 over beta e to the negative y over beta dy from 0 to k. So this is what you have to calculate. All right, so let's do one and see how it goes. Okay, so this integral, you already learned it from this integral right here. Okay, but this one is you go probability beyond. So your upper limit is infinity. But this one we want to go less than. So that's why we want to start from 0 up to k. But in terms of the integral, it will have the same final shape of the integral. It's going to get negative e to the negative y over beta from your integral. And then you just take the limit from 0 to k. Okay, looks good. All right, and then you substitute k in there because it has a negative sign. So let me substitute the lower limit in there first. So let me put the 0 in there with the negative turn positive. So that's mean I get e to the 0 minus e to the negative k over beta. You guys with me? I'm just trying to get the sign start from the positive sign and then followed by the negative one. Okay, very good. So that's it. So that is a probability then of the exponential distribution when y is less than some number. You're going to have the probability equal to 1 minus e to the negative k over beta. There you go. อย่างนี้โอเคไหมพอได้ไหมสนุกดีเนาะ Okay. So overall, once you understand this, now I can go back to my black ink here. So the probability of y less than k is 1 minus e to the negative k over beta. Subtract out the probability that y is less than k minus 1. So it's going to be 1 minus e to the negative k minus 1 over beta. Yeah, ไล่ไปเรื่อยๆ So we kind of know the shape of this whole thing. And 1 minus 1 just cancel. So what you have left is going to be e to the minus k minus 1 over beta. Subtract e to the negative k over beta. Something like this. Very good. เรียบร้อยเนาะ Okay. So this is how you can generate another distribution from the known distribution in this case. But because this time you only do it by do the binning. You just say, hey, if y fall within this range, you're going to name it some number, next range, next number, next range, next number. So it's still a simple, it's a generation of another random variable x. But in the future, next chapter, yes, we're going to build more complicated function. It could be like, x equal to y cube, x equal to log of y, x equal to y square minus something. Yeah. So that will be the topics of the function of random variable. That's next time. I mean, later. Okay. But for now, this is good. However, there is one special stuff that I want to talk to you with about this one. This is so cool. This one is just for fun. If you don't feel this is fun, then forget about it. อันนี้เล่าให้ฟังเฉยๆ It turns out if you carefully look at this one, it has an exponential in it. Yeah, all the time, pretty much. So what I can actually do, and I don't know if this is something can be done nicely or not. I don't know. อาจารย์พยายามจะดูอยู่เนอะว่ามัน easy to look at it or not. Yeah, I think that's fine. Okay, so what I'm doing over here is if I factor this one out, so because we know the k minus 1 is going to have the smaller number than the k, yeah? So that means I'm going to pull out the smaller numbers to the front, pretty much. So what I'm going to pull out is going to be e to the negative k minus 1 over beta. นี่อันนี้พอได้ไหม? Okay, so what you have left there, the first term is going to get 1, of course. And you're going to have to have the negative. The leftover is going to be e to the 1 over beta. Here we go. Okay, and then โอ้ยพูดดังขอโทษ and then let's look at the first term a bit. It has 1 over beta, pretty much, yeah? 1 over beta. Oh, there is a negative sign there. Sorry. Okay, there is a negative sign there. Is that right? เดี๋ยวนะอาจารย์เองก็อาจจะพลาดเองก็ได้นะ อันนี้ความครูอาจจะทำร้ายอาจารย์เอง There is some connection that is so nice. I want you to see it. Okay. 1 minus e to the beta. K minus 1. 1 minus beta. minus อาจารย์ทำอะไรผิดวะเนี่ย โอเคเดี๋ยวนะอาจารย์ขอดูตรงนี้นิดนะจะได้ไม่พลาดนะเดี๋ยวนะดึงอันนี้ออกมาอย่าง plus k minus 1 why it doesn't look so good นี่อาจารย์ทำถูกไหมเนี่ยเดี๋ยวอาจารย์ขอดับเบิลเช็คตัวเลขอาจารย์ก่อนนะอาจารย์อาจจะคิดเลขผิดทุกที minus k plus okay this is supposed to be negative sorry right there okay this is supposed to be negative plus beta โอ้โหอาจารย์เดี๋ยวอาจารย์อันนี้ขอติดไว้ก่อนได้ไหมคือมันเกือบจะคูลแล้วนะแต่อาจารย์กำลังงงว่าอาจารย์ดึงแฟกเตอร์อะไรไม่ออกมาแล้วมันทำไมมันไม่สวยอาจารย์ทำในหัวเร็วๆนะเดี๋ยวถ้านั่งทดเดี๋ยวมันจะเสียเวลาเพราะเราโอเค I'll work on this maybe during the break I just want to make sure that I get the factor out right okay but anyway at the end my trying is it turns out I can rearrange this whole thing is going to show you the geometric อาจารย์กะจะแบบเฮ้ยโอ้โหเป็นไงล่ะว้าวซะหน่อยfail it's almost but it's not okay it's manipulation almost there but เมื่อกี้อาจารย์คิดแล้วมันเครื่องหมายมันผิดอะ something must be wrong all right but anyway I'll work on this during the break all right but anyway I can rearrange this one and it will match the geometric distribution that we learned before and the geometric distribution before was like there is a success and fail and then you do your experiment until you hit the first success okay so with the whatever experiments in before that one all fails and then you hit the first success okay I haven't hit the success just yet at this point all right so we'll come back to that okay all right there's one more of course, that I want you to try. So this one is just the DIY. That is a numerical calculation now, so you should be able to try it. And pretty much seems like it's like substituting the numbers by base everything on the exponential distribution. Okay, it's just now evaluating the integral in the numerical way. So that should be quite straightforward example to try. Okay, sounds good. All right, so let's take a break right here. And during the break, I'll figure out that geometric distribution. My bad. All right, and take 20 minutes break, and I will see you back in about 10:35. Sounds good? Okay, all right. See you in a bit, guys. Okay. So during the break, I just check my manipulation, and I think it works out fine. Okay, so if you wow. All right, so if you wondering what I'm doing, was just double check the exponents. I was during before the break, I was got the different time, but it turns out to be okay. All right, so before we move on to the next problems that we would like to solve, okay, what I'm doing is just take a common factor. Okay, just like before อันนี้ฟังกันเล่นๆไปก่อนแล้วกันเนาะอันนี้ไม่ได้ serious มาก just for fun. So I said, so I saw this factor is the smaller one, so I pull it out to the front right here. There you go. So I'm left with just 1 minus e to the negative 1 over beta. Okay, and from there I can actually just rearrange just a bit. I don't know why I was confused. Maybe I tried to get it done to the e to the positive 1 over beta, but that's okay. It doesn't matter. I think you can see what is right here in front of you. So I can just rearrange this exponents in the front just a bit. So I writing e to the negative 1 over beta right here. And then I just pull k to k minus 1 outside to be just the multiplication factor of the exponents outside. And what you have left underneath, I mean, right here, is just another 1 minus e to the negative 1 over beta. Then, so if you look at this one, and then you just rename this one to be just q, whatever you have left in the last parenthesis, there is just 1 minus q. And this looks exactly just like q is your probability of failure, something like that. And then you fail for k minus 1 time until the last one you hit the success, which is 1 minus q, which is p. And this has exact structure of the geometric distribution. That's my point. แหมถ้าไม่งงเมื่อกี้ก็คงเรียบร้อยไปแล้วนะจ๊ะ okay, all right, but that's just for fun. But the note that I just want to get the message across is just, it turns out the geometric distribution has the memoryless properties as well, because it has the sort of like the exponential mechanism behind. So the geometric distribution is also memoryless. That's the kind of things that's kind of cool. Okay. All right. So this one for numerical example, I suggest you to try it. The other one that I really like better is this one here. And this is the one that we're going to do together. This one is more mathematical statistics. So let's take a look at this. So the length of time, y, necessary to complete a key operation in the construction of houses has the exponential distribution that's said as given, with the mean given to be 10 hours. The formula relates the cost of completing this operation. So that's the given cost, rely on the y. Find the mean and the variance of the c. So this is actually come in the concept of figuring out the expected value of c. Okay, and or you can think in terms of like the moment of c, many stuff going on. The reason I want to try this just to remind you what we can do. What we want, if you want to figure out the mean of c, so that's just expected value of c. So it's going to be the expected value of, now you drag in the whole expression right here, plus 3y squared. See that? Okay, that's pretty good. And that allow you to use the property of the expected value, just like we saw before. So you can spread this one out. For the expected value, you can just pull that constant out to the front. Okay, and then you do constant in the front. There you go. Okay. So what you really want to do over here is just try to figure out the first moments of the y, second moments of the y, on and on. Okay, sounds good. Okay, try again. So if you want to find the variance of the z, of the c, all right, so you need eventually to figure out the expected value of c square, right? We have been doing this all the time in the past. Once you get the expected of c squared, then you do the common formula e of the c square, subtract out the expected of c, the whole thing square, you get the variance. So in this expected value of c square, now that's gonna be a long one because you're gonna have to take c and you're gonna have to square them. Okay. All right. And that is gonna be quite a lot, but doable. A lot, but doable. So what you're gonna get is gonna be 100. Oh, I can write e of 100 for now, even though it's 100 eventually. So that's 100. Okay, the whole thing square though. That's square. Okay, let me write it like this. Okay. So don't want to sort of cross too many steps. So I'm just have to square them. Oh, wow, I got ขี้เกียจทำกันนะ Okay, 100 square plus you square this term 1600 y square 9y to the fourth, and then you have the cross term. You're gonna have 8,000 2 หน้าหลัง yeah. So the 2ab 2ac 2bc on and on. So you have the whole of the sixth term that you need. So there will be 2 480 deep. Okay, here we go. All right, plus 2 of the b and the c, so you get 240y cubed, and then 2 of the a and the c, you get 600y square. Here we go. So these are the expected value that you need to figure out. Oh, okay. เอาจริงนะเนี่ย Oh, what's wrong? We can also do, yes. Okay, there is a comment saying that for the variance, we can do the variance of the c, so you can split it out from one to the other. Yes, eventually. Very good. All right, so your friend just say, or you can manipulate this right away if you want. Yes, very good. All right, same thing. All right, that is the point that I want to make. So with that, okay, if I sort of agree with you, you still need to figure out the variance of, that will be the term of variance of y squared. So if you spread this one out, okay, so it's a variance of 40y plus 3y squared, right? So that means you still need to deal with this, the variance of y squared, which means you cannot get away from y to the fourth power. โอ้เดี๋ยวโทษทีนะมีคนบักอาจารย์มากเลยแป๊บหนึ่ง give me 1 second here. Okay, wrong number. โถจี้ซะ Okay จ้ะ all right, so that means you still need to worry about the variance of the y square, which means you're gonna have to deal with the expected of y to the fourth power anyway. นี่โอเคเนาะเข้าใจเนาะ so my point of this one is just saying that you have to figure out the expected value of y square, of y cube, and y fourth. Seriously. Okay. How can we do that? All right. And of course, you can sort of complete the whole detail of stuff, but let me show you expected of y cube. Is going to be of course, the integral, just following the expected value calculation. Y cube, you squeeze in the y cube in your integral, followed by the PDF, which is exponential. They say that is the 10-hour with the mean right here. Yeah, is a 10-hour. So what you can say of this one is when you go back to this exponential right here, you already said the mean will give you the beta, okay, which is fine. Okay, so in this case, the beta is 10. So that's good. Just put it here. So it's going to be 1 over 10 e to the negative y over 10 dy. Here we go. And then you do the integration everywhere, which everywhere means you start from 0, of course. In this one, it's positive numbers. Oogie, right there. So it seems like, well, Adan, do I have to evaluate this kind of stuff? If we have to do it, we might have to do it. All right. However, in reality, if you take a look at this form of the function, here, okay. So this one actually give you back, okay, อาจารย์ขออนุญาตสไลด์กลับนิดนึงนะจะงงๆนิดนึง here where we define the โอ้โหกลับไกลเลย here we go. If you go back and look at this, it has the shape of the gamma, pretty much. You see that? Because every time you deal with this kind of thing, you can always refer back to this gamma function. Because the gamma function is a product between the exponential, exponential back here, and the power function in the front. You know, เพราะฉะนั้นเนี่ย so what we can do is we can actually refer to this gamma function and reuse it pretty much right away. For example, that you just saw when you deal with y cube. Well, that is actually not too bad, because when you do the y cube, that means your alpha is going to be 4, something like that. And of course, you need some manipulation of the y a little bit, because the problem back there is not just purely y. It has some factor in the front. So let's take a look at what we have. Okay, so come back here. So what we have right here is, you compare this to the y to the alpha minus 1, e to the negative y dy. That is your gamma of alpha. นี้ทุกคนทันเนาะ? All right, so what you have over here is, of course, because when you have this, you still have to manipulate the y a little bit. Hey, I'm not sure if this is a good, comparison, I guess. Okay. Actually, maybe think of it this way. It's still not very easy, maybe. Yeah, I think that's fine. Okay. Okay. All right. So เนี่ยเบอร์อาจารย์ทดเลขในหัวนิดหนึ่งแป๊บหนึ่งโทษที all right, so what you have is you just have to deal with changing the random variable here. I mean, in terms of integrating factor here, to have the shape that looks just like what you have right here. It's y over 10 right here. Okay, so there is a little bit of room that you still need to sort of fill in to make sure that the integral looks exactly the same. Okay, so let me manipulate for this one for you so you see what I'm trying to do here. So what we have over here is, if I want y over 10, I want them all to look like y over 10. นี่ทันไหม? Okay, now, so what I'm trying to do here is this. Okay, let me show you with this. อันนี้โทษทีนะมันเบอร์มันทดเลขเนาะอาจารย์ไม่แน่ใจว่าเขียนแล้วจะเคลียร์หรือเปล่าเนาะ so when you have this, I have them all to look like the gamma function. So because it looks like y over 10 here, I need extra 10 down here. So I multiply by 10 over 10. นี่ทุกคนทันไหม? อาจารย์คูณ 10 หาร 10. I multiply by 10 divided out by 10. So it looks just like y over 10 over here. That's good. That's good. Now, when you look in the front, it's y cube over only single 10 here, but I need y over 10 cube. So I have to multiply by extra 10 square. So I have to multiply up here 10 square, just to doing nothing here, multiply by 1. So I'm multiplying 10 square, divided out 10 square. So with that, so what I'm getting is going to be something like this. Okay, let me write in green, integral y over 10 cube. นี่ทันไหม right? Because I already have 10 and 10 square, so I have 10 cube here, and I can merge it into the y. E to the negative y over 10 dy over 10. The limit still is good because when y equal to 0, y over 10 is still 0. When y equal to infinity, y over 10 is still infinity. So the limit of integration does not change. And when you look at this one, that's nice because now I can rename the y over 10 to be y. With me? Okay, and that gives me gamma 4 for this one. So this gives me the gamma of 4. So that means at the end, what I'm getting over here is, don't forget there is a factor right here that I have to multiply. So I have to multiply this thing with 10 cube total raised to the third. So it's going to be something like this. So what I'm trying to say here is, even though I'm not doing all of these, I mean, for you, but you can go back and try to check. You don't need to evaluate the integral yourself. You can refer back to this gamma function right here and try to just, adjust the parameters, adjust the variable to make it look like the gamma integral. And then you can just use the value of the gamma function and be done with. That's what I'm saying. All right. And everyone knows now the gamma of 4 is just 3 factorial. And then you can evaluate the value right away. So that's the cool things. Well, I would say it's not a cool thing, but that's the properties that comes with the exponential function. It's a family of the gamma distribution. So you can utilize the gamma function, which is like a ready-made integral for you. And if you can fit the form of your integral to make it exactly like the gamma function, then you can evaluate the value of this integral very easily. Okay นะพอได้ไอเดียเนาะ Okay, alright หวังว่าทุกคนพอเข้าใจมุมอาจารย์คือ it's okay, this question is tedious. I know it's maybe too much for the exam questions, but because we have time in class, so we would like to discuss this kind of thing because it's a mathematical it's not a trick, it's a mathematical procedure that usually can be found in a lot of mathematical analysis นะคือเราก็จัดรูปจัดอะไรเงี้ยโดยส่วนใหญ่เราไม่ไปdoing the pure integral start from zero again. We always try to use something that we have already known, try to build on top of that, manipulate, put this, put that, adjust a little bit, and it looks exactly the things that we have already known. So be done with. โหรู้เรื่องไหมวันนี้พอได้ไหมวันนี้ดูวุ่นวายนะดูมันเหมือนมันหลายอย่างนะแต่ว่า that's the nature of gamma function. The form of the function itself looks pretty bad. แต่หวังว่า from after this lecture you don't feel bad about this function anymore. It looks bad still, but at least you see the internal structure of this one and it's not that bad. It's just think of it, I mean, to me, it feels to me like it's the kind of product between exponential and power function. So that's just the main structure of this one. Okay, and back in the day, when you deal with this, you had to do the integration by parts นะโดยส่วนใหญ่เนาะเราก็ต้อง integration by part and then reduce the power of y down a couple of times on and on. But once you have the definition of the gamma function, and if your integral fits into this, voila, your integral is just fine. Okay, very nice. ทุกคนลองไปทำอันนี้เนาะยังไงก็ตามอยากให้ลองฝึกแล้วกัน test try it. This is very good. Just give it a shot and see how it goes. All right, very cool. Next. All right. Now, we have one last distribution for the continuous variable to talk about, and it's the beta distribution. And everyone look at this one. Oh, and you're probably asking, อาจารย์เอาจริงหรือเปล่า We already struggle with the gamma. Are you gonna start doing it on the beta? And okay, no. The answer is no. All right. Even though the beta comes in every time you have like proportion. So eventually we might have to refer back to the beta distribution every time we do the proportion of two random variables นะ หาสัดส่วน take the ratio percentage and stuff. Yeah, it looks as bad as gamma. However, the structure are a little bit different because right now it's two. You can see that there's no exponential in here. It's purely power function, but it's a power function of y and 1 minus y with different parameter. So that make it sort of complicated in a way because there's, if you look on the left, is the polynomial function, right? So it can go up or whatever is increasing function, and 1 minus y is going to be something in reverse and it's going down, and then you do the product between the two. So that's why you're going to get to something that's somewhere in between. And another thing is the denominator right there is the, of course, just like in the gamma, is going to be the integral between those two. The reason that the beta comes after the gamma is because it turns out this integral right here can still be expressed in terms of the products between gamma function. Oh, and it's still the two parameters density function. So you have still the alpha, and so you have the beta in your distribution. So we are not going to pursue this too deeply because, as you can see, the function looks pretty bad, and I don't think it's gonna give you anything sort of in terms of understanding the underlying mathematical procedure in statistics. So เอาว่าอาจารย์จะไม่ do anything about this. All right, but just to show you that there is another one that related to the gamma function, and it's the one that you come to this conclusion when you do the proportion between two things and those stuff. You might end up with the beta. And as here you can see now, because it's a competing between the rising of the y to the positive power and going down of the minus y, 1 minus y with the positive power. When you do the product between those two, you will hit the peak at some point. Okay, so they'll be rising when the y is small, and then it's going to be decreasing when y is big. Okay, and the mu and the variance is given accordingly. เพราะฉะนั้นไม่ต้องห่วง หลายคนกังวลว่าอาจารย์จะให้ do you gonna ask to find the mean and the variance in the exam for the beta distribution? No, I think this is way too far. Okay, and it doesn't have any sort of a reduced form, just like in the gamma, that when you have a special case of alpha equal to 1, you get exponential function, which quite easy to deal with for that exponential distribution. But for the beta, it doesn't look as nice. โอเคดีไหมเนาะเราจะได้สบายๆโอเคไม่ต้องกังวลมากแต่ underlying techniques, method of calculations, or evaluating techniques and other stuff works just like before. Just more complicated, of course. Okay. All right. So for the last part of today's lecture, we're going to look at the moments one more time, and everyone knows I'm going to lead to the moment generating function. Why not? All right. So the concepts doesn't matter if it's a discrete or continuous. They are analogous to each other. They're all the same. But the only thing that's going to be different now, you have seen, instead of summation, you're going to deal with the integral. So in terms of the definition or the naming or the terminology, still use the same thing. The moment about origin, we use mu prime. Okay. And if you want to find the moment at the order k, so you put the subscript k in there. So it's the expected value of y to the k about the origin is going to be mu prime sub k. Now, say same symbol notation, same thing. And if you want to figure out the kth moment about mean instead of about 0, So you can use just mu sub k without the prime. That's automatically say that is the kth moment about the mean. Okay. And sometimes you have a short sort of like abbreviated name, say it's a central moment. That's also possible. When you have a word central, it means you try to calculate everything around the mean value. Okay. So same definition works just like before. Okay. All right. And notation down here is still the same. Mu prime sub 1, that's just the regular mu. Mu 2, that's your variance. Perfect. Very good. All right. Nice. So with that, let's give it a shot. Like do a simple one. Try to figure out the moments about origin, yeah, of a uniform random variable. ว้าวมาทุกคนลองดูอันนี้วอร์มเลยแบบไม่ซับซ้อนเลยอันนี้ไม่ซับซ้อนทำได้แน่นอนทุกคน and it's good because it's flat. It's a uniform and it's uniform between 0 and theta. We have done this already back in the finding the mean and the variance of uniform random variable, so it shouldn't be a problem, but we look at in the perspective of the expected value. So mu prime sub k, okay, is going to be this one. We're gonna try to figure out like any k moments. We're gonna do them all pretty much. So it's gonna be expected of y to the k. Very good, very good. Okay, y to the k. And of course, every time you do this expected value, you take that y to the k into your integral, multiply by distribution density function, yeah, and then do the integral everywhere. But everywhere for uniform distribution is just between 0 and theta. ทุกคนงงๆอาจารย์มันก็ไม่ได้เวียนเลยนะ It's actually y, not the theta. อาจารย์ก็ว่าทำไมมันเตได้ equal to theta. Sounds weird. Okay, so it's y to the k 1 over theta dy from 0 to theta. Okay, that's better. Yeah, y equal to 1 over theta, not theta equal to 1 over theta. That's a weird one. All right. Okay. All right, very good. So what we have over here is now 1 over theta is just constant. I can pull it out. ดึงออกไปเลยจ้า All right. And now you only have to do the integral y to the k dy from 0 to theta. And everyone knows how to do this. It's just y to the k plus 1. And the exponent drop down in the bottom. Take the limit from 0 to theta. All right, very nice. Plug it in. So you have theta to the k plus 1 over theta k plus 1 right there. And of course, 1 theta cancel with this. So you get theta to the k over k plus 1. So now, actually, you have already found all moments. Every moment is here. Very nice. So that means for the mean, which is just the first moment around about 0, you just plug in k equal to 1 in there. So you got theta over 2. Perfect. This one is already known. The average of the uniform is just half theta over 2. All right. The variance and everything is fine, but for this purpose, we don't care about that anymore. So you can figure out the second moment, plug in theta squared over 3, on and on and on forever. Okay, so very good. So now you can figure out the expected value just like before, but now with the continuous random variable. So you do the integral instead of summation. Nice. พอได้เนาะ Not too bad. And if I want to extend this to what the moment generating function, you guys know what to expect. All I need to do is find the expected value of e to the ty. There you go. If you can figure out e to the ty, you're done. Pretty much. Do the same thing. And just to revise what we did before. Oh, you remember? Well done. It's just, okay, let me write it in black. Take the e to the ty, and then you multiply by the probability density function. Do the integration everywhere. Okay, do a quick reminder. What we did before was we try to expand this exponential term using the Taylor series expansion. Remember that? Very good. So you do the Taylor series expansion for the exponential to the ty. You're going to get 1 first term. Ty, that's the second one. Ty square over 2 factorial. Ty cube over 3 factorial, on and on. Okay, got that? That's the series expansion of the exponential. f of y is there. อันนี้ทบทวนเนาะทุกคนจะได้ถือโอกาส take the chance to revise what it means by the moment generating function. And when we have this now, I can do the integration term by term. So the first term is just 1 multiplied by f of y dy. The integral is everywhere, so just leave it there. Okay. Plus the second term, you get ty. So you get ty multiplied by f of y. And then you do the dy right there. The third term, you have t square y square. T square y square. F of y dy. Over 2 factorial, of course. And that is on and on. ทุกคนจำได้นะ Okay, this is what we did. All right. And what you can see is the first term just give you 1 because it's just an integral everywhere. Don't forget your integral is everywhere. Everywhere. First term, you integrate the whole density function everywhere, you're going to get 1. The second term, there is a t factor. You pull that t factor out to the front. Whatever you have left in your integral will be your first moment about the mean. There? Good. Third term, of course, you're going to be able to pull t square over 2 factorial out. And whatever you have left inside is y square multiplied by the density function. That will be your, let me zoom in a bit. That will be your second moment about origin. And now you can pretty much extend your series for the rest of this. อันนี้ทุกคนจำได้ยังโอเคเนาะ so that's why we said before this is the moment generating function because the expected value of the e to the ty has the information of all of the moments all the way to infinity. So the way to extract those mu sub k, yeah, the mu sub 1, mu sub 2, mu sub 3 primes is by differentiating and then substitute t equal to 0 out. นี่ควรจะจำได้เนาะ So what I'm doing, if I want to extract this mu1 prime, I just have to differentiate with respect to t once. So that's why I put the formula on the lower right corner right here. So you just differentiate the amount of order. If you want a first order, you differentiate that 1 time. If you want a second order, you differentiate 2 times. If you want third order, differentiating 3 times. But don't forget, every time you differentiate, you have to evaluate at t equal to 0 to get rid of the higher order term after your differentiation. So that's what you had before with introduction of the moment generating function. So it works exactly the same with continuous random variable, except now we do the integral instead of summation. Very good. Okay. So if this is good, and this is just a revise what we did before, let's give it a shot. เอาจริงดิอันนี้ finale เลย ระเบิดเถิง So what we have over here is let's find the moment generating function for the gamma distributed random variable that we just learned today. If we can get this, consider it done. ถือว่าจบและเรียบร้อย I think we complete the infrastructure of everything. Discrete random variable, continuous random variable. We understand all the moment generating functions. What does it mean by the moments, the mean calculation, the variance calculations, everything for the univariates random variables, single variables. So that's good. ฟังดูดีไหมคือตอนแรกไม่รู้ว่าเราจะต้องสอบไกลขนาดนั้น อาจารย์ตั้งใจว่าจะได้ไม่ให้หนักมากสำหรับ midterm จะได้ ขีดเส้นไว้นี้ I just draw the line here that this is the content that we're going to include in the midterm. And after the midterm, we're going to start looking at the multivariates. เริ่มดู2ตัวแปรดู covariance all this stuff. It will be more fun. But I think this is about at good point to stop right here. But we'll see how to adjust this a bit. อ่ะทุกคนสุดท้ายแล้วสำหรับวันนี้ดีไหมจะได้ไม่หนักไปนะดูทุกคนวันนี้เงียบมาก It's like very quiet today ทุกคนยัง still with me อ่ะ alright okay พอได้อยู่นะ okay alright now try to find the moment generating function for this crazy gamma distributed and then of course I have some reference right here on the right so you don't have to flash back too much and you will be amazed at the end result นี่การันตีเลย wow at the end seriously มาทุกคนลองทำ หรือบอกอาจารย์ช่วยรีบทำเหอะจะได้เลิกเร็วๆหน่อย Okay all right first of all I already get things started for you when you want to find a moment generating function you have to figure out the expected value of e to the ty squeeze it in จัดไปเลยจ้า e to the ty and take the whole density function of the gamma distributed random variable plug it in there crazy y to the alpha minus 1 beta exponential to the negative y over beta over beta to the alpha and the gamma of the alpha do the integral everywhere there you go and the everywhere in our case is only positive for the gamma okay there's nothing defined for the negative value of the yไหวไหมเนี่ย ทำไงวะ this might not be too bad all right whatever constants can we pull out let me pull the beta and the gamma out first okay beta to the alpha gamma alpha these are just numbers what else do we have we have exponential and exponential why don't we sort of merge them into a single term why not let's do that so we have y to the alpha minus 1 exponential squeeze them in pull the common factor y so I have t minus 1 over 1 over beta y dy here we go that's not too bad and if I rearrange just a little bit to make it sort of like clean looking if you want because บอกอาจารย์ we have already discussed we try to keep things in the sort of like the same shape and all the style and all the things so let's sort of do that a bit so follow me here so I'm gonna do this beta to the alpha stay the same y to the alpha minus 1 looks good already I'm just gonna flip-flop things a bit there is a y right here but we need a negative y right more than positive y so I'm gonna keep the negative y in the front there you go okay so let me do this so it's the steps look like this so I'm gonna manipulate it like this take the negative sign out there you go all right and then I'm gonna throw this parenthesis down to the bottom so actually it's gonna look like this 1 minus beta t over beta and y see that and then I'm gonna flip 1 minus beta t down in the bottom so this whole thing will look like this it's a negative y over I have beta down here and then divided by 1 minus beta t you guys with me อันนี้เขียนให้มันตรงๆกันได้เนาะยังไม่ต้องเบี้ยว okay. so let's go like this นี่เลยเขียนเริ่มเทิมนี้เลยให้มันรู้กันไป wow เลอะกว่าเดิมนี่ไงเหมือนลบเขียนใหม่ okay So it looks like this มาคำถามอาจารย์อินทิเกรตตัวนี้ได้เปล่าถ้าได้นี่เราเลิกเลยไหมถ้า if you can get this then we call it done โอเคเดี๋ยวทำข้อนี้อีกข้อหนึ่งละ that's it for the day sounds good okay what do you think can you figure this out คำใบ้ is on the right คำใบ้ is on the right we did this already today so we did this when we try to evaluate the higher order expected value yeah we sort of we try to rearrange this integral to make it look like a gamma function again because it looks so close to the gamma function see it's y to the alpha minus 1 e to the negative y over something dy so if I'm gonna name this something this gone right here I have that gone right there so let's do it in blue I want this let me call this gone right here okay so I want gone down here as well one gone here and I want a lot of gone here yeah ทันไหมเอ่ย okay so the total amount of gone the stuff the blue stuff that I want is 1 right here and alpha to the minus 1 down here so I have to multiply back by that stuff alpha minus 1 and 1 more with me guys okay right so I just multiply back and divide it out so that means all I need to multiply in is that stuff to the alpha and I divided out that blue stuff to the alpha perfect I'm not doing anything but once I have that stuff that blue stuff plug it in there what do you get Oop. What is this oh what did I do oh sorry I think I hit something okay let's come back here all right here we go so with that what I'm getting is going to be oh sorry it's just right at that corner again here let me pull that one okay get out of the way here we go all right so what we want over here is going to be 1 over beta to the alpha gamma alpha that's there haven't touched anything but I'm gonna have that blue stuff to the alpha coming out let me write it in blue that blue stuff is 1 over 1 minus beta t the whole thing to the alpha that is the extra right here come here that's your extra I don't know does it look even worse but that's what it is okay and now your integral looks just like to the alpha minus 1 e to negative d ทันบ่ okay so now your y over that blue stuff right there I'm just calling so that is to the alpha minus 1 e to the negative d and what is this thing here of course this is your gamma of the alpha very good so this whole thing right here is just here is the integral of the alpha minus 1 e to the negative the thing I would call this gamma of the alpha Woo. Believe it or not so what do we have so we have here we go beta to the alpha over beta to the alpha gamma of the alpha, 1 minus beta or t, the whole thing to the gamma, with the extra gamma of the alpha. Everyone with me? Okay, so what we have up to this point is the factor in the front, just right here. Okay, the one that we just got, beta to the alpha is right there. 1 minus beta t to the alpha is right here. And we just got the gamma of the alpha right here. Cool, perfect. So this thing cancel, that thing cancel. So your moment generating function for gamma distribution is, here, let me write it on the side here, 1 over 1 minus beta t to the alpha. Wow, 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 wow. ไหวไหมเนี่ยอาจารย์ไหวไหม Okay, and of course the condition that we need is to make sure that the integral converge and everything. So actually we will still need the condition of this blue ball to be greater than 0. So that is a little bit of the condition that you need to impose on here, because we always stick with the positive is a non-negative function for the gamma. So that's why you still require that beta over 1 minus beta is greater than 0. So if you look it up in the table, there will be some extra condition imposed that the t must be has to be less than 1 over beta, on and on. But in reality, for our purposes, this condition is always sort of like can be met all the time. We shouldn't have any problem with the divergence of the function. เฮ้ยอันนี้โอเคกับอาจารย์ไหมเนี่ย All right, very cool. So that is seriously the form of the moment generating function for the gamma. It looks pretty clean. It's 1 over 1 minus beta t, the whole thing to the alpha. And remember the uniqueness of the moment generating function. So it means from now on, every time that you are given the moment generating function that looks like this shape right here, 1 over 1 minus beta t, the whole thing to the alpha, you can say right away, we are talking about the gamma distributed random variable. And you can even read the power, you know what the alpha should be. You read the coefficient in front of t, you know what the beta should be right away. And not only that, once you are given the moment generating function, from this, we already learned that it has information of all of the moments built into it. Let's do it. Expand the moment generating function for the gamma distribution into power series and obtain all of the moments of the gamma distribution function. Yeah. Okay, last slide, guys. Yeah. So now we know is 1 minus beta t to the negative alpha. That is your function that you want to distribute out. So you do the Taylor series expansion if you want. So you do expansion. So this expansion, you can think in two ways. You can think in terms of like the binomial distribution if you want, or you can think it's like it's a Taylor series expansion. So to more general purposes, I can say it's a Taylor's expansion. You do it. And everyone, all right, I think this is your job. Check it out. What is Taylor series expansion if you are not familiar with this? But the idea is you do first term, you substitute t equal to 0 in there, you get 1. You do the derivative once divided by 1 factorial, substitute the function on, and this is what you're going to get in the second term. So you're going to get alpha in the front, beta t, there will be t in the front right there. Okay, so that will be something like so. All right, so very good. So when you do this expansion, so you try to do expansions and then you do it everything in terms of the power series of t. Yeah, you try to do the expansion around the t. So that's what you need to do. And then you do the second derivative. So you're going to get the alpha and you're going to get the alpha minus 1 on and on. So you're going to get negative alpha and you differentiate one more time. you're going to get negative alpha minus 1 as a factor in the front. And then you substitute t equal to 0, and that is it. That's done. And then you say what you're going to get at the end is going to be the t square. Don't forget the chain rule. So you're going to get the factor of beta square t square over 2 factorial. There you go. On and on. So you just keep doing it. You get the third derivative, substitute t equal to 0 in there, divided by 3 factorial. You're going to get the third term out of it. On and on. อันนี้ทุกคนต้องไปเช็คนะทำให้ได้ Okay, so this is make sure that you know how to do it. Try. Try to find the Taylor series expansion for the 1 minus beta t to the negative alpha and see how it goes. But once you see this, it's almost done. The reason it's almost done because if you want the first moment around the mean, what do? For this case, you can look at it and it's pretty much right there. So that's just alpha beta. Nice. Okay, and if you want the second moment around about the about its origin, it's just right there. What the factor that's in front? So that will be alpha plus 1, and the beta square. On and on. Okay, that sounds good. So this one just for the purpose of revising the Taylor series expansion. However, in reality, sometimes อาจารย์ who would want to do Taylor series expansion every time? What you can do, actually, you can say mu1 prime can be found from you differentiate the moment generating function once. Okay, let me write it in terms of the derivative. dm by dt, and you evaluate t at 0. This is the most straightforward way to get to the higher, whatever orders moments of your random variable. So it's right here. See, so this is the quickest way, pretty much. You take the moment generating function, you differentiate number of times equal to the orders of the moments that you want to get. All right. So if you want the first moment of this one, you just differentiate once. Okay, นั้นลองทำด้วยกันดูเนาะครั้งหนึ่ง so what I have to do is just differentiate 1 minus b t to the negative alpha once. Don't forget to evaluate t at 0. อันนี้หลายคนชอบลืม Now, everyone needs to substitute t equal to 0 at the end. Otherwise, then you're going to get stuck with the t, which is not the mean. It's impossible for you to get the average of something to have some weird parameter that's still in there. Okay, so everyone's differentiating this. So you get negative alpha, 1 minus beta t to the negative alpha minus 1. Evaluate at t equal to 0. Don't forget the chain rule. When you differentiate this, you have to differentiate the inside, dip side. So you do the chain rule, you get extra negative beta right there. And evaluate at t equal to 0. 1 minus 0 give you 1. So that term of power of negative alpha minus 1 go to 1. So at the end, you get alpha beta, something like this. Okay, so doing the derivatives, I think, is the straightforward way that you can get to whatever orders of the moments that you want to evaluate. Okay, so once again, this is a must try because we haven't learned too many distribution right here. We have only uniform distribution, normal distribution, gamma distribution, and pretty much some special case of gamma distribution. So once you learn what are these moment generating function, you pretty much know everything. All of the characteristics of this distribution are known through moment generating function. Okay, ไหมพอได้เนาะ Okay, so I have 2 more left in terms of the slides, but you don't have to worry too much about this one because it's just a quick extension that we have already seen in the discrete type. So if you want to figure out the expected value of anything, even though that thing could be a function of y again, all you need to do is just squeeze it in and to try to evaluate this. So I have one last sort of exercise. Well, if you want to try this one, but it's not too bad in the sense that if you don't have to worry about anything, you just evaluate the expected value. Okay, and I don't want to push too much on this one because we're going to have to deal with multivariate variables, and you still have a lot of time to deal with this crazy integral and all this stuff after this chapter ก็จะบอก after midterm ก็ไม่แน่ใจว่าเราจะ midterm เมื่อไหร่ okay after this chapter so next time we're gonna move up to chapter 5 I guess so it's I think go along pretty well I guess yeah so we're gonna look at the multivariate probability distribution but more than 50% we're gonna reuse stuff that we have already learned from single variable but we just extend of course extend stuff to two-dimensional integral to double summation or you have to now learn about the dependency between those random variables so that will be some more stuff that we have to add on top of what we learned from single variable sounds good okay just nod your head a bit silence means yes okay all right so if you don't have any further questions so at least once again confirm the midterm is going to be quite far away okay it's almost a month from now okay so it's on the 18th and in the meantime we're probably going to have to continue with lecture but let's draw the line right here so we're going to have our midterm up to chapter 4 in our reference text okay and some topics that I skipped don't have to worry too much about those okay and exercises already up in the classroom don't forget to check those out okay? And I'll see you again next week take care of yourself and bye bye